themselves and give rise to everything that we see as it is today. So we have the three generations of the quarks and the gauge bosons, and then we also have the Higgs boson that gives mass to all the other particles except neutrinos. And even though the standard model is very successful, there are a few motivations that hint towards the need for a new theory beyond standard model. Some of these motivations are experimental in nature and some others are theoretical in nature. And of these, the two solid indications that hint towards the need for new physics beyond standard model are neutrino mass, as indicated by the various solar, atmospheric, and reactor and accelerated neutrino oscillation experiments. So according to the predictions of standard model, neutrinos are massless, but then from these oscillation experiments, now it is well established that neutrinos have a tiny non-zero mass. And and this is like one of the major motivations towards need for a new theory. And another motivation is the existence of dark matter, as indicated by various astrophysical observations. Now, these issues could be addressed either by extending the particle content, by adding new singlets or multiplets to the standard model, or by extending the gauge group as well, like, for instance, left-right symmetric model or grand unified theories. So now coming to the neutrino mass, so I'll briefly discuss like the seesaw mechanism. Like there are like various mechanisms proposed in the literature that attempt to explain the sub-eV scale neutrino mass. And one of the most popular mechanism is the seesaw mechanism. And according to seesaw mechanism, neutrinos are Majorana particles and lepton number is violated at a very high energy scale. So in standard model, one can construct the dimension 5 Weinberg operator from the lepton doublets and the Higgs doublet. And this Weinberg operator violates the lepton number by 2 units. And once the electroweak symmetry is broken, once this Higgs acquire a vacuum expectation value, this operator in turn can generate small Majorana neutrinos for the active-like neutrinos. And depending on how one generates this Weinberg operator, for instance, this can be generated by the tree-level exchange of right-handed neutrinos, and then it is called the type 1 seesaw mechanism. One can also have it by the mediation of scalar triplet or fermionic triplet. And in those cases, they are called type 2 and type 3 seesaw respectively. And so here, like, we will focus on the type 1 seesaw mechanism, which means that the neutrino mass generation is mediated by heavy right-handed neutrinos. And so this is the, so here, like, I have pictured the canonical type 1 seesaw mechanism, where neutrino masses are generated by heavy right-handed neutrino. And as the name indicates, it is the heaviness of this heavy right-handed neutrino N that gives rise to the lightness of the neutrinos, and which is why that name for this mechanism. So in this case, the light neutrino masses, like mu light, will be of the order of md square by mn, where mn is the Majorana mass of heavy neutrinos, and md is the Dirac mass term for the light neutrino with the heavy neutrino. So md is basically y phi v phi by √2, where v phi is the vacuum expectation value of the standard model Higgs, and y phi is the Yukawa coupling that connects heavy neutrino N, standard model doublet L, and the standard model scalar doublet like phi. Now, one thing here is that that's not so appealing about this canonical type 1 seesaw model is that it is not testable, because to get light neutrino masses of the order of sub-eV scale, one has to go for either large values of Mn, extremely heavy Majorana neutrino masses, if you assume y phi to be of the order of 1 or 0.1, Or on the other hand, if you assume Mn to be of the order of TeV scale, then the Yukawa couplings have to be really small, of the order of 10 to the power of -6 or so. And in both the cases, the model won't be testable, will be difficult to probe in the collider experiments, which has motivated to consider various low-scale extensions of the standard model that can give various testable low-scale extensions of the standard model that can give rise to sub-EV scale like neutrino masses. And an example is linear seesaw. And in linear seesaw, to the standard model, in addition to 3 heavy neutrinos n, one also adds 3 gauge singlet fermions s, and they have opposite lepton numbers. Nc and s have opposite lepton numbers. And like without getting into the details, like one can get one can write the mass term for the neutral fermions in this form, where mu is the full 9×9 mass matrix for all the neutral fermions of the model. And so one can get this texture like either from a global or local symmetry. But then anyway, like assuming the mass matrix has this form, the light neutrino masses will have this form, like as given here. And here we assume a hierarchy for the mass terms. So here, like we assume epsilon to be really small, and m to be of the order of TeV, and md we take to be of the order of 100 GeV. Now, like one major thing that we do in TeV scale seesaw mechanism is that we decouple the scale of lepton number violation and the scale of seesaw. For instance, in the previous case, this mass term Mn was the scale of seesaw, and it is also the scale of lepton number violation, because Mn is a lepton number violating parameter. Like it's the lepton number violating mass term for the heavy neutrinos n. Whereas now in the case of this linear seesaw, in this mass matrix, the only lepton number violating parameter is epsilon, whereas m conserves lepton number. So in that sense, the lepton number is broken softly by this parameter epsilon. And if we take epsilon to be 0, then the light neutrino masses are 0, and lepton number is an exact symmetry of the theory, making the model natural in two sense. And also, like coming to the heavy sector of this model consists of 3 pairs of pseudo-Dirac neutrinos. So by pseudo-Dirac neutrinos means they are like almost Dirac, but then this extra term break their Diracness, so making it Majorana. So they're like almost degenerate, like they have like 3 pairs of pseudo-Dirac neutrinos. Okay, now, so as I mentioned, like I mentioned that this term epsilon is really small. And can there be a natural explanation of this small epsilon? So one idea is that like epsilon could be generated radiatively, which is what we have explored in this work. So we have tried to generate epsilon at one loop, and this is mediated by dark scalars and fermions, as we will see soon. And by like we have tried to link dark matter and neutrino mass generation. And this is done in a similar spirit as that of the scotogenic model as proposed by Ernest Ma. And for those of you who are not familiar with the scotogenic model, so this is the diagram. Like in scotogenic model is also a radiative, is a model in which neutrino masses are generated radiatively. So in this, like in addition to the standard model doublet phi, there is also an extra doublet eta, which is a dark scalar. It doesn't acquire a vacuum expectation value. So the neutral component can also be a dark matter candidate. And as you can see in this diagram, the neutral component also contributes to the generation of neutrino mass. So once this phi 0 acquires a vacuum expectation value, one can have tiny Majorana neutrinos for the active light neutrinos. So here the symmetries of the theory forbids tree level coupling of nu, n, and phi. So thus we don't have the tree-level Dirac mass term, md. Instead, the neutrino masses are generated at like one loop level. So we have proposed a model in a similar sense, but in the context of a low-scale seesaw model, in the context of linear seesaw model. Now, coming to the model. So this is the particle content of the model. And we have shown the, so here I have shown the leptons as well as the scalar particle content of the model. Okay, so we also have a global lepton number symmetry, which we have denoted by U1L here. So the first row corresponds to the standard model charges, whereas the second row corresponds to the lepton number global symmetry. So this is the standard model lepton doublet, and these are the lepton singlets. Then these are the heavy neutrinos N. These are singlet fermions Si. Now from this is the standard model Higgs doublet phi. Now in addition to the standard model Higgs doublet, we also add a scalar triplet capital psi. Then we also have another fermion Fi, which we denote as dark fermion. So the last three columns corresponds to dark particles. So Fi, we call it a dark fermion, and eta and small psi, we call them dark scalars. So eta is a doublet and psi is a singlet. These are the lepton numbers. And from these lepton number assignments, one can see that like we can also, there's a like remnant Z2 symmetry. So the lepton number will be broken spontaneously by this scalar triplet, capital psi. Even after it is broken, there will be a remnant Z2 symmetry under which these dark fermions and the scalars are odd, whereas all the other particles are even under this remnant Z2 symmetry. So these are the scalar representation, as I mentioned, like phi and capital psi. These are the standard model doublet and the additional scalar triplet that acquire vacuum expectation values. And these are the dark scalars, the eta doublet and the psi singlet. And this is the Yukawa-Lagrangian. And because of these symmetries, the underlying symmetries, prevent tree-level mass term, especially one cannot have the epsilon term that I showed earlier at the tree level, which in turn means that the neutrino masses are like 0 at the tree level. Now, as we will see, the epsilon term can be generated at the one loop level. Before that, I would like to briefly discuss the scalar sector as well. Sorry for the clutter. But then, yeah, this is the potential. Without getting into it, like I just have to mention that there is an additional term that we are adding in the potential. This is A phi, which is a trilinear term in the Higgs potential, which we are adding by hand. And this term breaks lepton number, but then softly. We have added this extra term to avoid the presence of this massless pseudo-Goldstone boson, the massless Myron associated with global lepton number breaking. So because of this Fi term, the imaginary part of the neutral component of the triplet scalar, sigma I0, gets a mass term, as shown by this, like Fi V phi squared by root 2 V phi. So this is one thing, and like one could also have gauged this lepton number. In that case, that would mean addition of an extra complex scalar to break the lepton number. So we wanted to keep it simple, so we just went for this option, breaking the lepton number softly here. And in addition, I also wanted to show the mass spectrum in the dark sector, the neutral scalars. So in the neutral, in the dark sector, we have two CP even dark scalars and two CP odd dark scalars. So the first one, the real, corresponds to the real part of the dark scalars, neutral dark scalars. And this corresponds to the imaginary part of the neutral dark scalars. And one thing, like you can see that they mix among themselves, and this mixing, for example, in the CP odd and CP even scalars, the mixings are opposite. For example, if theta d is the mixing for the dark scalars, then minus theta d will be the mixing angle in the odd sector for the odd scalars. So which turns out to be important for our model. And this is coming because of the special charge assignments from the symmetries and the way the contractions happen. Now, in addition to these dark CP even and odd scalars, neutral scalars, we also have charged scalars coming from the triplet as well as the doublet. And then we also have neutral scalars from the scalar triplet and the standard model Higgs doublet. So yeah, this is the scalar spectrum. Now coming to the neutrino mass generation. So this is the full diagram for active light neutrino mass generation. So here, this part, the LS part, corresponds to the epsilon term. So here, once V5 and once like the 5 standard model doublet and the triplet acquires a vacuum expectation value, it will give rise to this term, epsilon. And then one can have like neutrino masses as shown here. And the expression for epsilon, like from this diagram, is shown as below. So the first term corresponds to the contribution due to the CP even scalars. The second term corresponds to the contribution due to the CP odd scalars. And you can see there's a relative negative sign between the two. And from the previous matrices, we can see their masses are exactly the same, actually. The CP odd and CP even scalars, they have exactly the same masses. But then they have opposite mixing. The theta D and theta dA, they are opposite to each other. So thus the two terms, in fact, gets added up, and we have a small non-zero contributions to epsilon from this part of the diagram, from this loop. So here, like we can see the non-zero neutrino masses arises because of the spontaneous breaking of the lepton number by this scalar triplet V chi along with the electroweak symmetry breaking. And yeah, so these are the features. So coming to the salient features of the model, like just to summarize the salient features of this model. So first of all, the tree-level contributions to light neutrino masses are forbidden by the symmetry. On the other hand, tiny Majorana neutrino masses arise at one loop within the linear seesaw mechanism, as we just saw. And I already mentioned, like lepton number is spontaneously violated by a small Higgs triplet vacuum expectation value. And this Higgs triplet wave has to be small so that it will be it will satisfy other electroweak precision observables, and especially the rho parameter. So which means that the wave of this triplet has to be small, has to be of the order of 1 GeV.
Excuse me.
Yes.
What is the symmetry of your model? What are
the symmetry is a global lepton number symmetry, U1L. In addition to the standard model symmetry, we have a global.
You have a major one.
Yeah.
What is the major one? What?
Oh, so no. So to avoid the Majorana, that's why we have broken the lepton number softly with a trilinear term. So yeah, to avoid the massless Majorana, so we have broken it softly. So yeah, so these are the two sources of lepton number breaking in the model. One is by the vacuum expectation, spontaneously by the vacuum expectation value of the triplet, and the other one softly by this trilinear term.
We are assuming that your scalar potential has a minima.
Yeah. Other than this, like all the other terms are just the invariant under this symmetry, both the global as well as the standard model symmetry. So just this A5 is the only additional soft breaking term that we have taken into account. So
okay.
Yeah. So yeah, so as I mentioned, so these are the two sources of lepton number breaking. One is spontaneously by the Higgs triplet wave and softly by the trilinear term. And thus we are avoiding the massless Majorana. Now, the model can also have large non-unitarity effects in the PMNS matrix, because now you can have large Yukawa couplings, Y nu of the order of 0.1, with heavy neutrinos of the order of TeV, which means large mixing. And this can lead to sizable rates of charged lepton flavor violating decays, as we will see soon. And also, as I mentioned, the dark particles run in the loop and thus contribute to neutrino mass generation. So here we can see the dark fermions. So like all the dark particles run in the loop. So the dark fermions, F also contribute to this loop generation, and also both the dark scalars, eta and small psi, like they are also important in generating this neutrino mass. So they run in the loop. In fact, like all the particles that run in the loop are the dark particles, are the dark particles from the dark sector, just the F, eta, and small psi. So that, and they will also contribute to, so they contribute to neutrino mass, and they will also contribute to charged lepton flavor violation, as we'll see in the next slide. And by linking dark matter phenomenology to neutrino mass and charged lepton flavor violation. So yeah, I just wanted to summarize some of the features of the model before going to some of the phenomenological implications. Now coming to charged lepton flavor violation. So these are the two dominant diagrams that contribute to charged lepton flavor violating decays. For instance, mu to E gamma. The first Feynman diagram, the one in the left, is a standard diagram, the contribution due to the charge current, the W mediated diagram. So here, like the nu and the heavy neutrinos n contribute, run in the loop, and they contribute here. Whereas the diagram in the right-hand side corresponds to the dark contribution. So eta, the charged scalar from the dark doublet eta, and the dark fermion F can also contribute to this charged lepton flavor violating decays. So here, like we have done some numerical analysis, and these are the predictions for branching ratio of mu to E gamma, which we have plotted. So we have plotted the correlations of branching ratio of mu to E gamma as function of the two different Yukawa couplings, Y-phi and Y-eta. So Y-phi is the standard Dirac Yukawa coupling, the MD, the term that corresponds to MD. So this comes from the Y-phi term because it's a coupling of Li nu and standard model Higgs doublet phi. Whereas this in the right hand side, this vertex comes from the dark contribution, the like Y-eta, which is the Yukawa couplings of standard model lepton doublet to dark scalar and dark fermion. So in the yes,
you jump from neutrinos to sharp leptons, and I didn't see anything about sharp lepton before. And so you're assuming certain things here about the coupling of the leptons to these F particles and all that.
Oh, okay. So this is charged lepton flavor violating decay. So okay, like I will show the Lagrangian once again. So the charged, the masses of the charged leptons, they are the same. They don't have any difference.
Yukawas, that's it.
Yeah, the Yukawa for the charged fermions. Yes, they are the same as in the standard model.
Only Yukawas.
Yeah, only Yukawas. They are the same as in the standard model. Yes.
Okay, that was a question.
But then there is also this extra neutrino Yukawa coupling with the charged lepton doublet. So the first term that you can see here, like Li n phi. Sorry. Just a second. Yeah, the two Yukawa couplings that are important are like the first two Yukawa couplings. So in the second Yukawa couplings, we have the charged lepton doublet and the charged. They couple to the charged component of eta, and so which is the second diagram here basically. So the second diagram, if you see the mixing of the charged lepton with the charged component of the eta. And the first diagram is the charge current contribution. So the light neutrinos mixes with active neutrinos and then contribute here. And this mixing of the light neutrino and the heavy neutrino are proportional to this first Yukawa coupling Y-phi. So that is why Y-phi contributes here, because here the mixing between nu and n is proportional to Y-phi dagger Y-phi. So Y-phi contributes here. and y eta contributes here to this. Whereas the masses of the charged leptons are exactly the same as in the standard model, just generated by the standard model Higgs doublet.
These new fermions are vector-like fermions?
No, these are like Majorana fermions. The extra F that we have added, like they are Majorana fermions. So that is also one thing. So here,
anomalies. I mean,
so yeah, it has the global lepton charge of the F is 0. So that we have also added this bare mass term for the Majorana fermion F. So yeah, F is a Majorana fermion. So yes. So yeah, these are the two diagrams. And we have plotted the contributions. So in fact, we have plotted the two contributions separately. So first, like I'll just talk about the cyan points. The cyan points are the charge current contributions, the contribution due to the first diagram, which we know. So that is why there is they have correlation only with Wi-Fi, because the charge current contribution depend only on Wi-Fi and they are independent of Y eta. That is why that correlation is absent in the right-handed diagram, whereas there is a correlation in the left-handed diagram. Whereas the blue region corresponds to the contribution due to the dark sector. So the dark sector contribution depends only on Y eta. That is why there's a clear correlation here, and that correlation is absent in the left plot. So we basically wanted to show that the contribution due to the dark sector can be really significant in certain parts of the parameter space, and making their importance in charge lepton flavor violation. Making their contribution charge lepton flavor violation important as much as the neutrino mass generation. So the pink shaded region are disfavored by the current bounds, whereas the black lane corresponds to the future sensitivity. So part of the parameter space can be probed in the experiment. So there is also another caveat, like we have plotted Yukawa couplings up to very large values. That was just to show the dependence, but then we know such large values of Yukawa couplings do not satisfy perturbativity. So yeah, there is actually a cut a little less than before 100. So the cut will be at 12 pi, because this is trace of Wi-Fi dagger. So there will be a cut at trace of Wi-Fi dagger at 12 pi somewhere here. And yeah, which probably we should give here. So yeah, these are the predictions for charged lepton flavor violation. And now coming to the dark matter phenomenology. So as I mentioned earlier, from the remnant Z2 symmetry, all these particles like F, eta, as well as this small psi, all of them are odd under this remnant Z2 symmetry. So any of the, like, we can have any of them as the dark matter candidates, provided their masses are light enough and making them stable. So we can have different scenarios. We can consider two different scenarios in which F, the lightest of F as the dark matter candidate, or the lightest of the neutral scalars from the dark sector as the dark matter candidate. So we have explored like both the possibilities. So first, if we consider the lightest of the F as the dark matter candidate, then this is the scattering diagram that contributes, that is responsible for keeping the dark matter candidates in thermal equilibrium in the early universe, and thus contribute to the reluctancity. And so in this case, like we have done some simplistic approximations. We have just assumed that it is diagonal, that Y eta is diagonal, and only this Y1 contributes to this scattering diagram reluctancity. So we have so this pink region, the shaded region, correspond to the points that gives the correct observed reluctancity. So here we have varied the mass of this eta, the scalar, from 200 GeV to 5 TeV. So other than that, yeah, this is the parameter space that we have obtained. And like one thing about this fermionic dark matter is that it's very difficult to observe, because this fermion do not couple to standard model Higgs doublet. It only coupled to the dark scalar. And this dark scalar does not mix with the standard model Higgs doublet. So direct detection is almost impossible in the general scenario. So one can also consider scalar dark matter candidate, which is much more constrained by the direct detection bounds because the scalar coupled to the standard model Higgs scalars. So yeah, so here we have considered the scalar dark matter scenario. So if we assume that the dark sector scalars do not mix them, I mean, they mix, if we assume that the mixing is not so significant, and we assume that the singlet is the dark matter candidate, for instance, the singlet psi is the dark matter candidate, then these are the dominant diagrams that contribute to dark matter reluctance, that contribute to the scatterings in the early universe and thus to the reluctancity. And in this case, if you plot the dark matter coupling to the standard model Higgs, so this lambda is the coupling of the dark matter. It's like dark matter, Higgs coupling. Lambda is that coefficient. And MdA1 is the mass of that dark matter. So then these pink points are the ones that satisfy the observed reluctancity. So the magenta points, the pink shaded region is disfavored by perturbativity bounds, whereas the region above the gray shaded region is disfavored by the direct detection bounds from Xenon 1T experiment, whereas the region above the blue line is what is the region that will be probed by Darwin in the future. So we can see there is a large region of parameter space that can be probed by Darwin in the near future. So here we have also taken into account the scattering to the triplet, both the charged as well as the neutral components of the triplet scalar. And we have varied all these masses from 200 GeV to 5 TeV. And we have also varied the coupling of the triplet scalar to dark matter from 0 to 4 pi. So yeah, these are the results that we have obtained. So yeah, these are the two results about dark matter. And yeah, this is the summary. So we have proposed a minimal model where neutrino mass generation arises at one loop level within the linear seesaw mechanism, where the loop generation is seeded by a dark sector. And as I mentioned, lepton number violation is seeded by dark sector involving 3 Majorana fermions and 2 types of dark scalars. We can also have observable rates for charged lepton flavor violation, and we also have rich dark matter phenomenology. So yeah, these are the summary. And sorry, yeah, it's a short word. But then yeah, it's interesting. So we were a bit worried initially because suddenly it looked as if these terms would cancel, but then we had this nice observation where the mixing of the CP odd and even scalars were opposite to each other and then gave rise to this enhancement in this epsilon term. And yeah, so that fits a minimal model with lepton number violation, with a spontaneous lepton number violation by the triplet chi. Yeah. And this Fi term is basically to avoid the massless Myron. So one can also gauge the U1 lepton number and consider a full-fledged version with an extra gauge boson or gauging the symmetry. So yeah, any questions, comments are welcome.
Thank you very much, Vishnu, for the very nice talk. Question from the audience?
There's a lot of other constraints you can put into the model. I mean, like G-2, etc. I mean, even leptogenesis and
yes, actually, so that's why I mean, one can consider leptogenesis in this model, and also there is this STU parameters, electroweak precision observables, all those things. So so as the initial work, we just wanted to focus on the model and then highlighting the significance of the model, and just to comment on charge lepton flavor violation as well as the dark matter phenomenology. But then, yeah, like a lot more phenomenology can be done here in this context. Yes, that is true.
You are mostly concerned about neutrinos. I insist on that because the others you put just Yogawas and stuff like that. I mean, so
Yeah,
it's mostly about neutrinos.
yeah. So, Claudio has a question.
Yes, I have a question. So,
Yeah, sure.
can you show me the term that explicitly breaks the symmetry that avoids the majoron? Right?
This A5,
Okay.
yes.
So suppose this this term is absent. Which field will become the majoron here? You will have to have.
Yeah, that is the this term, basically the imaginary part of the neutral component of the triplet scalar. So I have given the mass here. So this is the mass of the neutral component of this triplet scalar.
Right.
This capital triplet scalar. So this neutral component. So the mass to capital psi I0 is proportional to F5. So once you put F5 to be 0, that will become the majoron. So that will correspond to the massless coefficient boson.
Right.
Yeah.
But this ratio of V phi square over V
chi, yeah, V chi.
So because I suppose that the constant is something maybe order 1 or smaller or something, right?
Yeah.
But this ratio of VEBs, it gives you a mass of what order?
It's really high because V phi is a standard model Higgs vacuum expectation value,
right?
Whereas the triplet wave has to be small. It has to be of the order of 1 GeV from the rho parameter. So this is really large.
Okay. So it's like 100 times heavier than, say, the electroweak scale.
Yeah.
Okay.
Yeah.
I have another question.
Yes, please.
Related to what Ivan was saying, in the case of the mu to E gamma, things like that, you are studying that only to make sure that you are within the bounds, right? That's the idea.
I mean, yes, we are within the bounds, and also we wanted to show the importance of the dark sector, basically. So the dark sector contributions are also as important as the charge current contributions here. So thus, the dark sector kind of seeds neutrino mass, and of course, they are the dark matter candidates, as well as the dark sector couplings also contribute to charge lepton flavor violation. So we just wanted to point out this interplay of this sector. Yeah,
they contribute, but they don't, they don't contradict the current evidence. So.
Yes. So yeah, any other questions?
Guess not. Everything was clear.
More questions?
Yeah.
I will make just a quick comment regarding CLFB, that in principle other constraint maybe could be considered. For example, electron muon conversion in principle could be set bound, but usually it may be similar as in the bound for mu to E gamma. Maybe a stronger constraint will be from sensitivity, because here what is plotted in the pink region is the exclusion band from experimental, upper experimental band from make experiment, but when
Yeah.
maybe one can put sensitivity and it will get a stronger constraint. And regarding leptogenesis, I think I would expect it to be that the constraint will be similar as in most generic lowest cases of model, because we will have resonant leptogenesis arising from the decay of the lightest of the pseudo-Dirac neutral lepton arising from this linear seesaw mechanism, and the lightest of them will decay, and the three-level decay will have interference with the one-level contribution, and this will generate this epsilon parameter. Another possibility could be to have leptogenesis by the decay of the dark fermion into dark scalar, dark fermion into the dark scalar into right-hand Majorana neutrino n, and then this three-level decay is interference with the one-level contribution, vertex, and self-energy diagram can also be used to have leptogenesis. In that case, it will not be resonant.
Yeah, that could be interesting scenarios rather than the traditional ones. So yeah, the leptogenesis scenario could be traditional. Just that, yeah, the decay will be to the, in the current case, yes, yeah, it will be the standard resonant leptogenesis. True. So, yeah.
Some people do leptogenesis by decay of the scalar. This could be other possibility. There is like in China, I think his name is Pei Hong. I think he is one of and Pei Hong is as an author of a paper of double seesaw mechanism, as well linear seesaw mechanism. The paper that we were discussing in the meeting of the morning. Where resonant leptogenesis, he has some paper of three-loop radiative seesaw model, and he also considered decay leptogenesis induced by decay of the scalar. This could be another maybe approach that could be considered, for example.
Yes, people have studied. Yeah, I mean, Tomoyambi also has studied like generating Baryon symmetry from the decay of standard model scalar, like phi. So there was a paper. So,
it could be like this.
Studied. Yeah.
Or it could be decay from the singlets, for example. Or maybe baryogenesis by complex parameter in the scalar potential.
True.
More comments, questions from the audience? Any more questions, comments? If there are no more comments, if there are no more questions, we thank Vishnu for the very nice talk, and we meet at the next seminar.
Okay. So yeah, thank you. Thank you, everyone.
Thank you very much, Vishnu.
Yeah.
Thank you very much. All the people that attended and participated. Thank you very much, Vishnu, for the nice talk.
Okay. Yeah. Bye. See you in the office.
Bye. See you.
Yeah. Bye.
Bye.
Thank you.
Thank you.